continuity of functions. Better I say continuity of graph of function. If you are given the graph of function in this form, maybe exponential function or whatever, we can draw a linear function, we can draw a quadratic function. Between these 2 points, A and B, the graph of function is continuous, and we will see that the function is continuous from A to B, where the x coordinate of the point A is A and B is B. So we will say that the function y equal to fx is continuous in A to B. It is better to say we can draw the graph of the function without lifting our pen or pencil to plot the graph of function. If without lifting our pen or pencil in the graph of a function, then it must be continuous over there. So I am defining a function this manner. This is 1 and 2. The graph of function is like this. At x equal to 0, it is 0. And when x less than 0, the graph of the function is like this. Okay? Let me write it mathematically. Fx equal to for x greater than 0, 0 for x equal to 0, and say this point is, this is 1, 2, and this is -1, -2 this way. This is -1 for x less than 0. Were you able to plot the graph of function without lifting your pen or pencil? We have plotted this part because for x less than 0, -1, it continues this way. At x equal to 0, it is 0. For x greater than 0, it is 2. But when you are plotting this, around 0, you can see that we have to lift our pen or pencil to plot the graph of function. So this function is not continuous at x equal to 0. Okay? What about this function which is very familiar to you, that is fx equal to mod x by x for x not equal to 0 and 0 for x equal to 0. This is famous because you have done it as signum function in class 11 syllabus. So for this signum function, if you rewrite the function, it will be x by x. I mean 1 for x greater than 0, minus x by x, -1 for x less than 0. Remember it, 0 for x equal to 0. In your textbook class 11, the graph of function was also there. So let me try to plot the graph of this function. When x equal to 0, it is 0. It is 0 here, similar to previous one. This function is also not continuous at x equal to 0. Okay? If I try to draw the graph of this function, say fx equal to mod x, then graph of function will be what? As you are habituated with the graph of this function, I am plotting this thing first. See, starting from anywhere on the left side, if we continues plotting the graph, this arrow means it continues towards right, arrow means it continues towards left. So this function graph is continuous everywhere. It is continuous for all x belongs to R. We'll say that. So graph of the function will help a lot. Let us go by this one, fx equal to modulo x. If you plot the graph of this function, as you are familiar with this function also, so I am going to plot this. The graph of the function at integral points is not continuous. This you can see. And we'll say that the function is not continuous at the integral points. This point is 1. When you are trying to plot this, between 0 and 1 you can plot. If you say that it is continuous between 0 and 1, continuous between 1 and 2, I agree with you. But it is not continuous on R. Not continuous on R as it is discontinuous at integral points. Okay? It is discontinuous at integral points. So I hope with these basic functions, you have understood what is continuity of a function. You'll be able to plot the graph of function without lifting your pen or pencil, then the function is continuous. If you cannot do like this, it is not continuous over there. Okay? Let me illustrate a few functions here, which if I try to draw, it will be wastage of time. Let us try to understand the continuity of these standard functions. A constant function that you know very well. A constant function is of the form fx equal to a constant. This remains the constant always. This is a constant, same constant. This function, this arrow means it is continuous towards right, continuous towards left. This one, this is of the form fx equal to ax plus b. It is also continuous everywhere. And this function is of the form fx equal to, say, x square minus 2. This function is also continuous everywhere. A cubic function which intersect the coordinate axis, I mean x-axis at 3 points, it is continuous. This is also continuous. Quadratic function, no. This is a function of 4th degree. I mean biquadratic function. Quartic function, better to say. And this is quintic function. Graphs of these functions are continuous everywhere. So these are continuous functions. And what's the special name for these functions? These are all polynomial functions. We'll state that all polynomial functions are continuous everywhere. You can say everywhere on R. These are all real functions. They are continuous. So polynomial functions are continuous everywhere. Trigonometric functions, are they continuous everywhere? If you analyze the graphs of these functions, fx equal to sin x, it is continuous on R. Agree or not? This function we can plot without lifting our pen or pencil. It is a continuous function. Is this a continuous function, fx equal to cos x? This is also continuous function on R. This one, see, this function is cosec x. It is not continuous at which point? At 0. At 0, you are plotting the graph of this function, but when you go there, you have to lift your pen or pencil. Then the graph of this function is not continuous. We'll say that function is not continuous. If you say that, won't it be continuous between these 2 points? Yes, of course. If you define some domain for this function, many are there, it is continuous over there, but not continuous on R. This one, this function, not continuous on R. Why? Because it is discontinuous at minus pi by 2, pi by 2, 3 pi by 2. Similar is the case for tan x. This is also not continuous at those points. So, fx equal to tan x not continuous on R. This is not continuous on R. Alright? So, be familiar with the inverse function also. Is it true that you are going to be discover inverse function now? No, you have done inverse trigonometric functions. So what I am saying, this function fx equal to sin inverse x will not be a continuous function. If you try to plot the graph of these functions, it is better to say they are continuous in their domain of definition. Okay? Fx equal to sin inverse x. In the interval, that if you take the interval from -1 to 1, it is assumed to be continuous, because it cannot accept the value beyond 1 and less than -1. So this function is continuous on domain of the function. It is continuous on its domain. Tan inverse x graph is this. This one also continuous on the domain. Continuous on domain F. All these functions. Even sec inverse x. No. This is not continuous. Why? Because you see, when you are going to plot the graph of this function from infinity to this point is perfectly alright. Sec inverse x. But for this point, when it is going to be, say, this one is origin, no? This origin sec inverse x, it cannot accept the value between -1 and R. This point is -1, this is -1 part, and this is 1 part. It cannot accept the value between -1 and 1, so it is not continuous on R. It is continuous -infinity to -1 or 1 to infinity. Similar is the case of cosec inverse x. It is continuous from this point 1 to infinity, that -infinity to -1, you can plot the graph easily, but at x equal to 0, I mean, if you take any value between -1 and 1, it is not continuous there. This is 1 again, no? This is -1, it cannot accept the value over there, so not continuous. This is not continuous on R. This is also not continuous on R. Separately, if you say it is continuous from -infinity to -1, it's okay. From 1 to infinity, it's okay. But it is not continuous between -1 and 1. It's alright. So graphs of these functions, these two functions, inverse trigonometric functions, are not continuous on R. And these two continuous on domain, they are also continuous on their domain of definition. Keep this thing in your mind. Logarithmic function. For b greater than 1, graph of log is this. For b less than 1 and greater than 0, graph of the function is this. So again, if I say that this is continuous for x greater than 0. In fact, its domain f is 0 to infinity. It is continuous over there. Both the functions continuous in the domain. Exponential function like y equal to 10 to the power x, 5 to the power x, whatever you take, e to the power x. If x is greater than 0, it is gradually increasing. These exponential functions, it may be decreasing also. The graph of the function may be like this also. For x less than 0, we can define. So these functions, exponential functions, are continuous everywhere. Okay? The function we have taken here, that y equal to a to the power x form. Okay? A may be greater than 1, a may be less than 1. Then the graphs will be like this, and it is continuous everywhere on the number line. Because it's continuous, no? Put arrow over there. If you put arrow here or arrow, it continues forever. So continuous everywhere. Rational functions like 1 by x minus 2, minus 1 by x minus 2, whatever you take, these functions are not defined for x equal to 2. So the function is not continuous at x equal to 2. In general, for any rational function of this form, say fx equal to ax plus b by cx plus d is not continuous when x equal to minus d by c. Okay? There may be product of two factors, like the rational function we are taking this form, x plus 1 by x minus 2, x plus 3. It is also not continuous, at which points our denominator vanishing. Continuous at x equal to 2 and minus 3. If you plot the graph, you'll find there are asymptotes at x equal to 2 and x equal to minus 3. Now, every time you cannot draw the graph of function and then decide continuity of the function at a point or on an interval. So you have to be habituated with some analytical concept which also can be derived from the concept we are now discussing, that is graphical method. Like, you cannot say this function is continuous at x equal to 0. Why? This function at 0 it is defined, at the point say 0 comma 2 it is defined. I mean, beyond 2 it is, beyond greater than 0 it is defined, less than 0 it is defined, but it is not defined at 0. Why? The geometrical meaning was you cannot draw the graph of function without lifting your pen or pencil. So not continue at 0. For any function, if it happens that this function, say we have taken fx2, we have already done x greater than 0, 0 for x equal to 0, minus 1 for x less than 0. Try to understand from here. If someone asks you to calculate the limit of function, then limit x tending to 0 minus fx is what? Minus 1. Limit x tending to 0 plus fx is 2. And limit x, I mean f0, what is its value? 0. Limit does not exist. The function is not continuous. But only existence of limit will not assure you the existence, I mean continuity of the function. Only existence of limit. Like if I show you this example here, say the graph of function is like this. At this point, this is the point A. Suppose this one corresponds with some value, say 5. These are two parts of the function we have plotted the graph. And at x equal to a, the function takes this value, that is 0,6. Limit x tending to a minus fx. What will you say? This is equal to 5. Limit x tending to a plus fx. This is what? This is 5. But what is fa? That is 6. Are you able to draw the graph of function here? By by using a pen or pencil when you are not lifting your pencil? No. And from the definition of limit, the limit is existing at this point x equal to a, but the limiting value is not equal to the functional value. You are saying that limit x tending to a minus fx equal to limit x tending to a plus fx, but this is not equal to fa. We are not able to plot the graph. We cannot make the limiting value is equal to functional value. Limit exists. You can see that here limit x tending to a fx is 5, but fa equal to 6, which is obviously not equal to 5. So the function is not continuous. So what is the essential condition for continuity of function at a point? For continuity of function at a point, for continuity of a function at a point x equal to a, you must remember limit x tending to a minus fx, limit x tending to a plus fx must be equal to fa. Or simply you can write, you need not calculate the left hand limit, right hand limit always. If you observe that limit is existing over there, then you simply state that limit x tending to a fx is equal to fa. This is the essential condition for continuity of a function. That limiting value must be equal to functional value. If we don't get, then it will not be continuous over there. Okay? If we want to say continuity in an interval, see, continuity in this open interval. Continuity in AB means the function, y equal to fx, it is continuous at all points between A and B. If C be an arbitrary point belonging to AB, then for continuity, limit x tending to C fx must be equal to fc. Okay? Limit x tending to C fx must be equal to fc, then it is continuous. Now, how to state continuity in a closed interval AB? How to say that? because I am discussing continuity at a point. Continuity in a closed open interval is fine. You have taken the open interval this manner. You are saying that continuity everywhere between A and B. This is A and this is your B. Continuous everywhere in between A and B. C is an arbitrary point for you to prove that it is continuous. Then it is continuous everywhere. But what about this closed interval? A and B both are included over there. Then continuity in AB is ensured if the function fx is continuous in AB, then fx is continuous on AB. You know how to check? This is the first condition. Number two, fx is left continuous at A, and number three, fx is right continuous, no, sorry, fx is right continuous at A, and it will be left continuous at B. At B. Because my aim is not to plot the graph of function for continuity beyond B. If you try to plot the graph of function here, this you take an arbitrary one. So just up to the point B we'll check. So for that, we'll be checking right continuity at A. What does it mean? This means limit x tending to A plus fx must be equal to fa. This is right continuity at A. And for this one, limit x tending to A minus fx, sorry, this is B minus fx, x tending to B minus fx should be equal to fp. Then it is left continuous at B, and we are able to plot the graph of function without lifting the pen or pencil. Hope you have understood. Continuity at a point, continuity in an open interval AB, and continuity in the closed interval E, comma B. Got it? This is the time to apply these simple concepts of continuity to solve some standard textbook problems. Prove that the function fx equal to 5x minus 3 is continuous at x equal to 0, minus 3 and 5. You go by the definition we have just learned, that left hand limit, right hand limit and functional value. There is just one part of the function 5x minus 3. You can verify it by plotting the graph of this function, but we'll be following the definition that limit x tending to A minus fx equal to limit x tending to A plus fx equal to fa. If this condition is valid, if these three are equal, then the function is continuous at the point. So here, if you try to find limit x tending to 0 fx, this is limit x tending to 0, 5x minus 3, nothing to eliminate from numerator and denominator. It's not rational function. It's a polynomial function. You simply put the value 5 into 0 minus 3 minus 3. And what is f0? We need not get the left hand limit, right hand limit here. f0 is what? This is minus 3. Therefore, the function is continuous at x equal to 0. When you are answering MCQ for board, no need to calculate. Just a polynomial function is everywhere continuous, that we have seen in the graphs of several polynomial functions. It's a polynomial function of first degree. So what will be your trick for MCQ? That just put the tick over there, it is continuous everywhere on R. Okay? And about minus 3, the same manner, you just check limit at x equal to minus 3, limit x tending to minus 3 fx, you find x tending to minus 3. So this is 5 into minus 3 minus 18. And a for minus 3 is what? This is also minus 18. They are equal, so the function is fx is continuous at x equal to minus 3 also. Similarly for x equal to 5, and the technique for MCQ will be the same. Since it's a polynomial function, it will be continuous. The same manner, you can do it for second one. That it's a quadratic polynomial. For MCQ, we put tick, it is continuous everywhere. And for board examination, you will simply find the left hand limit at 3. No, just limiting value at 3 and functional value at 3, they are equal. Okay, examine continuity. Examine you can do by plotting the graph. Examine you can do by using this analytical method. Okay, let us go for this one. Is this function continuous at x equal to 0, at x equal to 1, and at x equal to 2? See, if you are confused, then I'll tell you, let me do this sums for all three parts. At x equal to 0, what part of function is there? We'll be observing that only. For x equal to 0, we'll be taking this part. What is limit x tending to 0 fx? This is limit x tending to 0 x, so 0 only. And f0 is what? Since fx x, f0 is 0. Therefore, fx is continuous at x equal to 0. What about at x equal to 1? At x equal to 1, you have to test left hand, right hand, and functional value. For x equal to 1, the left hand limit is what? Limit x tending to 1 minus fx. This is limit x tending to 1, less than 1 is this part. So value is 1. The right hand limit will be what? Limit x tending to 1 plus fx. 1 plus is there, that is for 5. It's a constant function. So put 5 over there. And what about f1? F1 is, you'll be taking this, no? For x less than or equal to 1, you'll be taking that part. So f1 is by putting x equal to 1 over there. So what do you observe? The left hand limit is not equal to right hand limit. Although left hand limit is equal to functional value, but you must check all three are equal or not. So what will be your comment here? The function is not continuous at x equal to 1. Clear? Now at x equal to 2, what do you observe? At x equal to 2, at x equal to 2 means it is greater than 1. For x equal to 2, we will be taking fx equal to 5 because it is defined that manner only. And it is a constant function, continuous everywhere. Definitely it is continuous at x equal to 2. But if they ask you to check it, then you will write formally just for your board examination, limit x tending to 2 minus fx is 5. This is limit x tending to 2 plus fx, and this is f2. Same thing. Always it is coming 5. So it will be continuous there. We are discussing continuity at a point. We have just done continuity at point. Here, they have asked you to calculate continuity, overall continuity of the function. So it is better to say we have to check continuity in the interval. Go for that from 6 to 12, and then 26 to 30. 30 will be continuity in the interval, and these are at the points. Okay. So when you are going to consider continuity for these functions, you have to consider continuity in a interval. Okay. So how do you answer this? The best way I will be telling you. Number 6 I am going to answer for you. You see, this is polynomial function, x less than equal to 2. It is continuous everywhere before 2 and equal to 2. I mean, that interval minus infinity to 2. It is continuous for x greater than 2 also, agree or not? Because it is polynomial over there. But continuity doubtful at x equal to 2. So your statement will be like this. If x being a polynomial function is continuous for x less than 2, where fx is equal to 2x plus 3, and continuous for x greater than 2, where fx is 2x minus 3. This is also polynomial function. But problem arises probably at the point x equal to 2. Why? Because nature of function going to be changed. We doubt continuity at x equal to 2. So in an interval there is no problem. You state that continuous everywhere before 2, continuous everywhere after 2, but at 2, but continuity at x equal to 2 is doubtful. Why? Because the function is changing at that point. That point you calculate limit x tending to 2 minus, that is left hand limit. Which part of the function are you going to take? You are going to take this part only, isn't it? So you are going to check that point where just limit x tending to 2 minus fx. This we are going to check. This will be limit x tending to 2. 2 minus means 2x plus 3. You take 2 into 2 plus 3, that is 7. This is the left hand limit. What about the right hand limit? Limit x tending to 2 plus fx, and this is 2x minus 3. So 2 into 2 minus 3, that is 1. F2 even I did not see only. Why? Because limit is not existing. If limit don't exist, the function will not be continuous. Although if you find F2, That will be done with the help of this thing, that is 2 into 2 plus 3. 7. So limiting value and functional value, I mean left hand limit and functional value matching, but left hand limit and right hand limit not matching. This implies the function is not continuous for x equal to 2. Continuous at x equal to 2. You can state that also. Okay? Now let us check another problem from here, which you might get some trouble. I'm not talking about 10, 11, 12, 13. These are the same concept problems. Problem may arise in number 7, number 9, where modulus function is involved. And today's class I will be discussing the technique you have to adopt for answering board MCQs as well as descriptive questions. So for this kind of function, wherever there is modulus, you rewrite the function here. So we are solving say number 7. We rewrite the function. Rewriting the given function. Fx will be x plus 3. Can I take? Because if you go by definition of mod x is x for x greater than 0, 0 for x equal to 0, minus x for x less than 0. X less than minus 3 means it is less than 0. So you cannot take plus over there. You have rewritten the part which you were supposed to do. The rest of the part will remain the same. Minus 2x, and this is and for board descriptive question, again you will start the same manner, that is, being polynomial function, it is continuous everywhere without continuity at the points minus 3 and 3. So this function continuous, same statement, being polynomial function, it is continuous for x less than minus 3, x greater than minus 3, less than 3, and x greater than 3. Without continuity at which point? Minus 3 and 3. Continuity at x equal to minus 3 and x equal to 3 has to be checked. How to check that? At x equal to minus 3. Left hand limit is what? Minus 3 minus 0 fx. You just write minus 3 minus. Minus 3 less than minus 3. Which part is there? And what is the answer to this? 6. Right hand limit. Which part should I take? This part. Minus 2x, this is going to be minus 2 into minus 3 is 6. Do I need to proceed? Yes, because functional value we need. Then only we can say the function is continuous or not. What is the value of f of minus 3? Just look at this. Put x equal to minus 3 here only. 6. The function is continuous at x equal to minus 3. Clear? Similarly, Composite function. The idea you have done it in function chapter. F and G are real functions such that f compose G defined and the function G is continuous at x equal to a. Means its domain of definition. This I have mentioned so many times in today's session. A function is continuous in its domain of definition, always. At a point A is a point and f is continuous at G, then f compose G is continuous at x equal to A. So in simple word, if there are two continuous functions, their composition also continuous. Okay? They have asked you to check this one so that this function fx equal to cos x square is continuous. How to check? 31. See, we are going to take two functions. Let gx equal to cos x and hx equal to x square. What is your opinion about cos x and x square? Both are, they are not mentioned any interval over there. So we'll think about the whole number line, that is for all real values of x. Both gx and hx are continuous functions. Agree or not? Both gx and hx are continuous for all x belongs to R. Now, G compose hx, let us calculate that. G compose hx will be what? GOHX we have to find. This is nothing but G of hx. This is nothing but G of x square. But gx is cos x, so cos of x square. It is continuous for all x belongs to R. Okay? So the composite function continuous everywhere. 32 is also a simple one. You start this manner, that gx equal to cos x and hx equal to mod x. You know, cos x and both of these functions, both are continuous on R. Both are continuous on R. So their composition, that is HOGX, is what? That is H of Gx, that is H of cos x, that is mod of cos x, is also continuous on R. Okay? Similarly, you can check it for sin mod x. Mod x minus mod x plus 1. There will be no point of discontinuity because it is difference of two continuous functions. Hope the simple approach I have used to solve textbook sums today's class you have understood. And this session was completely for your board preparation. Okay? How to answer the questions I have tried to explain as much as it possible for me. Thank you for staying with me.